Hi everyone, this is Aman Soni. I'm a software developer here at GeekyAnts and specializing in AI, of course. And so today's topic is going to be the computer vision from pixels to insights, how to drive insights from a pixel. Okay, so we'll be covering everything from scratch and to the point where we'll be utilizing the YOLO and the complex deep learning models as well. Before jumping directly into the concepts, let's discuss why do we need the CV on the first place, right? Let me start with a story. This is a guy who is like doing his computer science, his degree in computer science, of course. He's from a farming background, right? But from a very young age, he have seen this. Like his father used to struggle with uh, the point where the disease ate up their entire crop, right? And of course, it was a huge issue for them. It used to drain up all their wealth. So, what he did was he created a system that would detect early how would the pest or insects can affect their crop, right? So they utilized the power of computer vision, and they would easily detect the disease and the pest earlier before happening, right? Then after that we have the story of a store with a very small short front. They just launched their product. They just launched their like entire set of outfits, but the front they got in the mall, it was very short, but they had to like showcase their outfits in order to sell them, right? So what they did was they hired some computer vision engineer, and they created some screens that would like act like a mirror. And when each of the like passerbys like pass by, and it would automatically show the clothes, their entire clothes, their outfits on their body. So suddenly people start to notice it, and eventually they started coming in and checking out the outfits that they have, right? With a swipe, with a single swipe, they could easily change the outfits and like how they look in that particular color. So it helped them a lot, and they are doing wonders now. Perfect. So this is the role of the CV, and we'll slowly approach to the point where we'll be building entire thing from the scratch as well, right? So in this particular GeekSpeak, we are going to cover the content of the fundamentals and the image, some basic image processing techniques as well, right? Starting from the image representation, that how would image be represented in a like a vector database or everything like that. And also we'll see about the filtering and the edge detection with the image segmentation as well, right? So let's just dive right in. Let me start with a very basic thing. That how would the computer understand an image? As a human being, we have the power of visualization, so we can easily visualize, okay, so this is a person, this is a cat, this is a dog, right? But as a computer, how would you make it understand like what is going on, what kind of thing is going on, right? So we have multiple formats of the images. For example, the one that we have selected here is 1 bit, which is a binary image. That means we have only two values. For example, if we have like only two shades, that is one is white and another one is black. So in this particular image, you can see there is a matrix that is associated to it, and all the white pixels are represented as a 1, and all the black pixels are represented as a 0, right? So that means we can easily like tell our computer that okay, we have an image which is of two colors. But in general scenario, what happens is we have a lot of shades of black and white. We are still on a grayscale image, right? We have a lot of shades of black and white. So what we did was, instead of using two colors, we shifted towards the 8-bit grayscale color, right? So here we have 256 total colors, and starting from 0 to 255, right? So 0 would represent the black, and as we are approaching towards 255, the white intensity get increases, right? Perfect. Let us understand that with this particular image as well. As you can see, we have extracted a matrix out of it. And in that particular matrix, as you can see, the points, the pixel, those were whites that are really close towards 255. But the pixels, those are on the darker shade that are related to 0 as well, right? So this is our grayscale image. But we don't always use the grayscale image. We have to go to we have to see the entire color frames that are present there, right? So what will happen if I keep the matrix same, and instead of using the grayscale, I make it red. Instead of using gray, I make it red. So the matrix is same. If we are shifting the entire matrix to red, the image will look somewhat similar, but the shades of image will be red instead of the black and white. That means not only red, we can use multiple colors as well, right? So that we can stack up the arrays. For example, we have a single array, right? I'll copy that array and I'll create a three-dimensional array out of it, right? I'll stack each array on top of each other, and those are arrays that have different color values. For example, my first array is of red color, and then after that proceeding one is the blue, and then after that it is green. And we know these three are the primary colors that can create an entire image, that can create any color that you want, right? So after combining these three images, we are approach towards our colored image, right? So let us see that in our code sample as well. So this is our Python script. First, I have imported some modules, some necessary modules. Image IO is just for reading the image that is present in our system, and then after that, matplotlib is used to project what kind of picture it is, right? So first line, we are taking the input from the system. Then after that, we are plotting it on the graph. As you can see here, what we got as output is it's an RGB image, and it is of dimension 15 cross 15. That means our image is of pixel size 15 cross 15, and the maximum value that is present in the image is RGB value that is present. It is 255, and the minimum is 0. Here you can see there is a white portion present here, and also a black portion present here. So white will be 255 and the black will be 0, somewhat around 0. Okay, let's move further, and let us also see the characteristic of that particular image in order to understand that properly, right? So we have the output of an image which is of shape 562 cross 960 cross 3. What does this 3 signifies? We know in two-dimensional we can showcase any kind of image, right? But what does this 3 refers here? 3 is nothing but the number of channels that are present in here. So the height is 562, the width is 960, and the dimension of the image is 3, where 0 is represented as a red color, green is represented as a red is represented as a 0 pixel value, and green is represented as the first index, and the blue is represented as the second index. Combines up, it goes to 3, right? Okay, so let us play with some pixels as well. We don't only view image, we can also edit an image, right? So let us alter with the pixels as well. So in here I have selected the same pixel, and I have selected the row here, right? As you can see, from 50 to 150, these are the number of pixels that I have selected here, and in the red color frame, because I have also given 0 here as well, and that is equal to 255. That means it is on the full intensity of the red color, that all the pixels that are present in this particular range will be of red color. Perfect. So I have shown that in the image as well. Then we have plotted the image. As you can see, we have got a thin straight line of the red color here. That just represent that we can play with the matrix, and we can get the results out there on our image as well. Perfect. Okay, so as we are moving forward, let me clear some basic things in the image, this computer city. So there is a huge difference between a convolution operator and a multiplication operator. Multiplication you might have always heard, like you might have heard previously as well. So convolution operator is very different from the multiplication operator, although they look very similar. So what convolution operator does is, you have a specific size of matrix, right? And you have a kernel as well. Kernel you can select of any size. For example, I have selected 3 cross 3 matrix here, right? So what kernel does is, it rotates over entire image. It rotates over the entire matrix that you are having of that particular image, instead of multiplying the matrix with each other, right? So it will traverse through each of the pixel, and then after that it will give you the results. This is how the convolution operator generally works, right? So there are some predefined like filters as well, and you can create them as well. You can play with them. So there is a normal image, and we are like convoluting a box blur filter over it, and the result that we are getting as a matrix is a blurred image. Perfect. We have always done these kind of things in our PixArt as well, right? But what if, let's suppose we are playing a game. Let's suppose we are playing Forza, and we know when we like accelerate our car, the background always get blurs and the car always like remain sharpened, right? So how do we achieve that? Or you can say, when you click a picture from the DSLR, it always have this effect on you, and the background gets blur, right? So how do we achieve that? So for that, there are two techniques that we have to use. Basically, first one is the edge detection. In edge detection, you are doing nothing but creating a filter that can traverse over your entire image and create some edges, right? Create the edges of the entire image that you are passing in. Perfect. So there are three types of edge detection. So first one is the Canny edge detection, second one is the Sobel edge detection, and the third one is Laplacian edge detection. The only difference is this: in Canny edge detection, as you can see, there is very high level of edges that are shown here. But as we are approaching towards the Laplacian edge detection, the number of and the intensity of the edges gets increases. It is again like considering the small edges as well, not only the bigger one but the smaller one as well, right? Okay. Then selective blur is equals to edge detection plus blur filter, right? That means we have detected the edges of our entire object, right? Now we can select that particular object, and we can select the particular background that we want to do the blur, right? So we have like selected the background, and we have applied that blur filter that we have already seen, right? So from here we can get our result, our desired results. Perfect. And there is one interesting application that removes the noise from your image. You might have already seen like some companies are marketing it as an AI, but it is not actually an AI. It is just like they are using the median filter or some kind of customized filter that they have made, and they are traversing that entire kernel over your particular matrix, or you can say the image as well, right? So here you can like, I am like telling you, you can try multiple different kind of kernels as well. So to get like hang of the matrix that you can create from these images. Perfect. So let's focus on image classification, object detection, and image segmentation part. So these are the backbone of like creating different kind of objects and different kind of images from a particular like AI, or you can say deep learning models as well, right? So starting from very basic, which is image classification. Okay, so let us consider a scenario in which we are taking an input from a lunar surface, right? And from that input, we have to classify either this particular image is having some kind of potholes into it or not. As we have to traverse our rover on that lunar surface, so we need to know either this is having some kind of pits or not, right? So we trained our model, we got the image classification. It will only classify it like, okay, it is having some kind of pits or potholes into that particular frame, or it is not having any kind of potholes there, right? That's good. That will be very beneficial for us. But there is a problem. Let's suppose, like, if we want to traverse our rover onto that, we need to know which area of that particular image is having some kind of potholes, right? So that we can traverse our rover instead of that particular pothole, right? So here comes the concept of object localization. Object localization is nothing but image classification plus the rectangular box that you are seeing here in this particular frame. So here it can easily identify and localize that, okay, there are 2 dogs and 1 cat is present, right? So that is perfect. It will do good for us. But there is one more scenario. Let's suppose we have to calculate the probability that either our rover is going to fall into that particular pit that the lunar surface is having, or it will go straight and there will be no damage to it, right? So for that, we need to calculate the area in which the potholes are present, or you can say we have to calculate the area which is straight, which doesn't have any potholes or something like that, right? So here the image segmentation comes into the picture, where the object, or you can say the number of potholes that we have discussed earlier, will be given a certain area. Okay, this is the area in which the potholes are there, or you can see in this particular frame there are particular cars that are parked aside, and there is a road present there. So from here you can see, okay, the maximum road is like empty and you can drive here, and there are very less number of vehicles. And on the lunar surface as well, like you can easily classify, okay, so these are the as many as number of potholes that are present here, and we don't have to we can calculate our probability from there. Perfect. Okay, so this was the entire basics of what we planned for this particular GeekSpeak. And in the upcoming parts, we'll be discussing the feature extraction and the descriptors, and also we'll be leveraging the power of machine learning and the deep learning in the particular computer vision as well, right? From this series will be going to be beneficial from scratch to the point where we'll be creating our YOLO and the deep learning models. Perfect. All right. So thank you, everyone.